Hello, welcome back. Lecture 36 today. So, we shall continue our discussion on nanoscale MOSFET, general purpose nanoscale MOSFET. Last class we discussed about drain induced barrier lowering, and we also talked about the threshold voltage roll off in highly scaled devices. So, today we will continue on the discussion and we will move to other topics here. So, the whiteboard here. So, the next thing to understand is a charge quantization effect or a quantum capacitance effect. So, you know the inversion channel that forms in a MOSFET is like a triangular quantum well. So, there is a 2D electron gas, and that is very similar to what we talked about in gallium arsenide HEMT, except that here there is no modulation doping, by the way. Please remember that. Just a triangular quantum well, you have subband levels E1, E2, etc. This is your Fermi level, correct? So, there is this wave function and there is the centroid of the distribution of electron. We have already discussed that in the context of L-GaN-GaN HEMT, L-gas-gas HEMT. So, it is very easy to understand. So, there is a delta D. This delta D is the spread of the 2D electron gas or the centroid of the 2D electron gas. So, whatever oxide thickness you have, this is silicon dioxide, or maybe you can say this is hafnium oxide, and this is a T oxide, and the 2D electron gas has a spread of delta D. So, the gate to the channel distance is actually not Tox, but it is Tox plus delta D. Now, this does not, because this is a few nanometer, as long as this is large it does not matter, and that is why people have neglected that. But now if your thickness is highly scale, you know, it is in the same order as delta D, then it matters, then you cannot ignore that, which means your actual capacitance is not epsilon naught epsilon x by Tox, but it is Tox plus delta D. So, the overall capacitance is reduced. This is the effect of charge quantization in the quantum well, or you can say quantum capacitance effect. So, because of the centroid of the electron distribution or electron cloud distribution, the effective gate capacitance reduces, and because the effective gate capacitance reduces, your gate loses the control on the channel to some extent and your threshold voltage increases. This is not a desirable effect. Okay. So, keep this in mind please, because this is we'll come back to that in the next slide, I believe. Then there is something called polysilicon. So, polysilicon is polysilicon, it is highly doped silicon, but it is not metal, which means there is a depletion width that forms inside the polysilicon gate, because at highly scaled devices the fields that you sustain are very high, the vertical field specifically. The vertical field can be very high, and there could be, this is finite doping, because of the finite doping in the gate polysilicon, the high vertical field will create or lead to some depletion in the polysilicon gate. Now, if the polysilicon gate, you have a gate here and then you have an oxide and then you have this delta spread delta D, already you have a spread oxide plus delta D. Now, in the gate if there is a depletion, say this part is depleted, then some part of the gate is depleted. So, that XGD, I can say that is the gate depletion, that will also have its own capacitance, because the effective gate is now this. So, this extra increased depletion in the gate metal stack leads to a further increase in the gate to channel distance. The total distance D is now XGD plus delta D plus Tox. Okay. So, the combined effect of this polysilicon gate depletion and the charge quantization or quantum capacitance is that the overall thickness of the gate dielectric is increased. This is what I am talking about. It reduces the overall capacitance, and it is not good, because it is not by design, you know, you are losing control on the gate. So, capacitance equivalent thickness is defined as equivalent oxide thickness plus this quantity. You see, this is dielectric constant of silicon by dielectric constant of oxide into the polysilicon depletion, the depletion in the polysilicon gate plus delta D. You see, delta D is finite, you cannot help it, and this polysilicon depletion is also finite. In long channel devices, your vertical fields are not so high, so this quantity is very negligible, close to 0, and this quantity does not matter because your oxide thickness is pretty large. So, in that case this quantity becomes almost negligible, but not in highly scaled device. And EOT, I already defined EOT, that you know, if 24 nanometer of hafnium oxide has an oxide equivalent thickness of 4 nanometer of SiO2, that is what equivalent oxide means. So, it is basically the thickness of the high K dielectric that you are putting into epsilon of silicon dioxide divided by epsilon of the high K dielectric. So, in this case of hafnium oxide, if your dielectric constant is 24 and this is 4, okay, and you are going to use say 12 nanometer of hafnium oxide, okay. So, this will become 2. So, that is 2 nanometer of SiO2 is going to be exactly same as 12 nanometer of hafnium oxide. Now that is amazing. 2 nanometer will leak a lot because of tunneling effect, 12 nanometer will not leak a lot. So equivalent oxide thickness is 2 nanometer for a 12 nanometer oxide. Okay. So that is important to keep in mind. As I keep telling you, with higher vertical field because of a reduced scale devices, your mobility degrades and you adopt strain channel. Of course, the vertical field could be as high as 4 to 5 megavolt per centimeter, which is pretty high. And so although your source and drain are also scaled down, your source and drain and then your gate, your source and drain is also scaling down, and because of that the field here, the field in the source drain also starts kicking, it also leads to velocity saturation. So the field in the lateral direction, in this direction, the field in this direction is never as high as the field in this direction in the oxide. Okay. So field in the lateral direction could be say 0.2 megavolt per centimeter, but field in the vertical direction in the oxide could be around 4 megavolt per centimeter, or at this interface the inversion charge forming area could be close to 4 megavolt per centimeter. Okay, it is crazy actually. So the mobility degradation actually is more strongly affected by the vertical field than the lateral field, or than by the velocity saturation effect due to the lateral field. See, if your mobility did not degrade and if you did not have velocity saturation, then your drain current goes as Vg minus Vt square. It has a quadratic dependence on the gate voltage. But when the current is undergoing velocity saturation and there is mobility degradation, then the current goes as just Vg minus Vt. It has a great significance. So initially what it means is that if you plot Id versus Vg, in the traditional case your Id will go something like that, right, your Id will go something like that, but now in a highly scaled device with velocity saturation it will go linearly. Now you can say that the linearity improves GM and etc., but those things are important for power amplifier, we are not talking about that. So a flat GM is precisely not the point that we are trying to get to here, just saying that your IDVG curves kind of assumes linear. However, real FETs are partially velocity saturated, not fully. So what you get is a combination of the square Vg square and linear Vg. What I mean is that you can see in the next slide, here is the diagram. So you can see this is your drain current, okay, and on the x axis is your gate voltage. So you can see that this is a quadratic region, this part, because your current is varying quadratically like this, and you can see that here, you can see that here. Beyond that this is linear, your current is varying linearly at higher gate voltages, so it has a slope like that. So this part is linear and this part is quadratic. The region where the quadratic behavior is holding good is very narrow, it is around 0.2 or 0.25 volt on the gate max. This region is only 0.25 volt, for instance, it is very low. Okay. So this is for 90 nanometer node, for a 90 nanometer node only 0.25 volt is the maximum range typically you can get where you have a square law being valid. Okay. And threshold voltage can also vary, by the way, the threshold voltage also can vary a lot. So maybe I will remove the annotations here. Okay. So what is happening is that designing circuit with a fixed gate overdrive is not viable, not tenable. Why? Because as you can see that the quadratic relation does not hold true except for a very small range. Threshold voltage can vary a lot, when the drain voltage is changing, short channel effect. There could be process variation on threshold voltage because of highly scaled device dimension, your process becomes very complicated. People use immersion lithography, there is lot of extreme UV lithography, there is lot of process complexities that come that over a large area of wafer there could be process variation impact on threshold voltage. So RF MOS design or circuit design could no longer be done with just a constant Vg minus with a gate overdrive or W by L ratio, that is not feasible, which used to be in the case of analog circuits long back. Okay. So people use a constant IDS design technique. So you fix the drain current, and you design around that. Basically you can change the gate voltage accordingly to get the desired drain current, okay, output drain current. Once your gate length is frozen. See, you will implement it in a foundry in a certain gate length process. So, you can say that I will use 65 nanometer process. So, your gate length is fixed now. So, once your gate length is fixed, then you bias the gate such that you get a desired drain current per unit width amp per mm. So, you want certain milliamp per micrometer or microamp per micrometer, that is your drain current you want. To get that drain current some x, okay. To get that drain current you have to fix the gate bias and you get the drain current. Once you get the drain current per unit width, you have to multiply it by that width to get the absolute current. So, you can multiply it, the two parameters to play with, one is the gate width and one is the number of gate fingers, how many gate fingers you are going to get. So, the number of gate fingers and the width of per unit gate, these are two very crucial you can say parameters that are available to a circuit designer to design an RF CMOS based circuit. Okay. So, you fix the per unit per mm current and then you go to the absolute current by, or you absolute GM you need by playing with W and N. Okay. So, this is very important to understand there. Okay. So, now that we have discussed all of this, we can, I think we can talk about parasitic resistances now, okay, because these are very important for RF application. So, you know RS and RD are the source and the drain resistances and they are a nuisance because they degrade the performance. Okay. Source resistance in particular can affect the GM, drain resistance will of course affect the on current, the on resistance. So, they are very bad, they should be as low as possible. And these resistances, source and drain access resistances, they vary as 1 by W, which means if you increase the gate width, then your resistances will come down. So, if you have a 1 millimeter gate width, suppose the resistance of the source or drain is it is a contact basically, it is a combination of contact resistance, access resistance, and there are so many other things, extension resistance, tip resistance, etc., they are all expressed as ohm millimeter or ohm micrometer. Say this is around 0.1 ohm millimeter. Okay. So, if you have an 1 mm device, you have to divide it by 1 mm to get the absolute resistance, which is 0.1 ohm. Now, if I had a 5 mm device, then the absolute resistance is 0.1 ohm mm divided by 5 mm. This will be 0.02 ohm in absolute quantity. So, a wider, this is W, a higher larger gate width will lead to a reduced absolute source and drain resistances. That is why source and drain resistances, they scale with 1 by W. Okay. Typically at 90-65 nanometer nodes, the normalized per unit or width is basically 0.1 to 0.2 ohm millimeter is the RS and RD value. And what are these different components? There are different components. There is this resistance of the source contact diffusion region, there is the resistance of the source drain extension region, there is current spreading resistance, there is strip resistance of the accumulation layer. Do you know what this mean? So, let us look at an image to actually understand what it means. I will come to that. So, this is your the zoomed image of the source drain part. You see this is your RSCO, okay. This part is your RSCO, which is your resistance of the source drain contact diffusion region. So, this is basically the resistance of the actual N plus the region that you are putting, it is the resistance of that as the current is flowing, it is the diffusion region resistance you can say. There is Rx. What is Rx? Rx is the resistance associated with the source drain extension region, source drain extension region. So, because this is extending outward, that is an extension region resistance that you are going to get. This is RSP. RSP is the spreading resistance, the current is spreading out, and so there is a resistance correspond to the current spreading, and this is the accumulation resistance, like there is a charge channel there. So, you can say this is the trip resistance or the resistance of the channel there. So, these are 4 components of the resistances in the source drain. Okay. To have better resistance control or minimize the resistance, your doping profile should be abrupt at the channel end of the source drain extension, which means this doping profile here has to end abruptly, that is what it means. Okay. Now, each source and drain finger may have many vias. These are via holes that you etch to take it on the top. Do not think of this via as the backside substrate via that we talked about in high power amplifier based transistors in gallium nitride or gallium arsenide. This is not that via. This is a via, but this is not a true substrate via. This is a via between different dielectrics, interconnects through which you are going to take the metal out one by one on the top. Okay. So, each via tungsten plug that we discussed will also have a resistance which is R con, contact resistance of that via. If you have n con number of contact vias per source drain stripe. So, if you have say 3 contact vias, suppose this is 3, this number of 3 source drain vias are there when one stripe, then the overall resistance will be given by R con by n con. So, with higher number of vias the resistance comes down. So, this is whatever resistance you have will be divided by 3. If there were 4, then it will be 4. So, the resistance corresponding to the via number will keep decreasing as the via number increases. Okay. So, keep that in mind. So, this is again the top image here shows an overall schematic of different parasitic resistances associated with say 65 nanometer or 90 nanometer node general purpose scale MOSFET. You can see that there is, apart from these resistances that we discussed just now, and this is the R con by the way, the resistance in the via hole by the way. There is also resistance from the drain to the bulk or the body. There is a resistance from source to the bulk or the body. There is a resistance of the well. There is a resistance from the contact this point to the body. So, there are different kind of resistances, and this is from the side view. If you look from the top view, it looks like that. The drain, and these are drain vias. This is a drain via, this is a drain via, this is a drain. There are 3 drain vias. So, the drain to the, this is the bulk, okay, this body, there is a resistance here. Similarly, source to the bulk here, the 3 resistances in the source and this is bulk. So, resistance is there. This is the gate resistance. Okay. So, this is the gate resistance, we will come to that very soon. So, these are different parasitic resistances that are there in the nanoscale MOSFET. Okay. I already talked about this. Gate resistance is a very interesting feature because gate resistance directly affects your Fmax cutoff frequency of the power gain cutoff frequency, it affects the noise performance, it is very important. So, either you can have gate connecting from one side which is this, or you can have gate connecting from 2 sides which is this, and you can see there are 4 via holes here. These are all via holes in the source or the drain, the via holes in the source or the drain. Okay. So, if you have just, and this is a contact via here by the way. So, if you have just gate feeding from one side, then this is the expression for the gate resistance. If the gate feeding from both sides, then this is the expression for the gate resistance. Remember the gate resistance as in the gate metal resistance. Okay. And gate metal resistance scales as W, because you can think of this as a bar, you know, as a bar. So, there is a cross sectional area and then there is a bar. So, this is your W. So, you can say that resistance is actually rho L by A, L is here W, area is this cross section area, that is the thickness of the metal into the gate length. So, with higher width of the gate resistance goes down, very bad for noise and Fmax, and with lower LG also the gate resistance goes down. So, if you go from 65 nanometer to 45 nanometer, because the gate length is reducing, you will get higher and higher gate resistance. Okay. So, that is very important. So, that is why with higher scale devices your W also has to come down. That is the reason with high frequency millimeter wave devices the W has to be very small. So, what are these expressions? This R con, as I told you, the resistance of the each contact via. This is the number of contact via. This is the sheet resistance of the metal, and this is L. L is the gate, you can say the length, I would say not this length here basically, and F is the number of actually fingers that you have. Okay. How many fingers? So, here you have NF equal to 3, you have 3 fingers. So, that is NF equal to 3. Wx is this, you can see that, you know, this gate pad is sitting some distance away from this active area, no, that is your Wx. Wf is your gate width here, and that is divided by 3. In this expression the only difference is that this is divided by 6 because you are feeding from both sides, and this is 2 times NF because you know you are feeding from both sides. Okay. So, please keep that in mind. So, this is the now this gate resistance expressions have been derived using a distributed resistance network. You know, if you remember, a gate in a microwave frequencies, the gate resistance cannot be treated as a lumped element. You have to invoke the distributed resistance concept, that you know inductance, resistance in series and capacitance in parallel, people do that. But even if you ignore the inductance here, the gate resistance is a distributed resistance you know concept, you have to use that model. So, in this image you can see that people are using a distributed gate resistance model. You know, you have one type of, here you have only one gate pad, you can have a separate gate pad, and that will be you are feeding from the both side, by the way. So here you can see that as the current is flowing, each of them is a incremental or a delta W, you discretize into delta W, and each of them has this resistance RGI. So it's a distributed model that you are invoking, and this is the mathematical, to develop the mathematical model, this is the network that you are talking about. You can ignore the inductances, but there's a resistance of the gate, then there is a capacitance, there's a resistance, there's a capacitance, there's a resistance, there's a capacitance, correct. You are ignoring the inductance. So by doing that you actually get this formula, okay. You get this formula for doing one side and two side, of course you get this different formula, okay. So this is your gate resistance, distributed resistance, or concept is being used here, and these equations are some simple expressions for expressing the gate resistance. Now that we discuss resistance, we can come to capacitance. Capacitances are very, very important in any RF devices. So the intrinsic gate capacitance, the true gate capacitance CG, has two parts. One is your gate source capacitance, one is your gate drain capacitance. So apparently in triode region, linear region, triode region is basically when you have ID versus VD, the output characteristics, it goes something like that, right? Correct. This is the triode region. So this is your triode region, the linear region, you can say the triode or the linear region. Apparently the gate resistance, people have shown that gate resistance split equally between source and drain, gate capacitance is split equally between gate source and gate drain capacitance, half. Each of them is half of the gate capacitance. However, in this saturation regime, this is a saturation regime, 2/3 of that of the total gate capacitance is just gate to source. So CGS dominates, while CGD or gate drain capacitance is almost 0, and there are other elements, fringing and other things that might take up the rest of it, but gate source capacitance is the dominant. It takes about 70% of the total gate capacitance. Just please keep that in mind, okay. Maybe I will remove the annotation here. So you can see that okay, where is that? Okay. So this is your schematic of different capacitances. These are fringing capacitances. CF is a fringing capacitance. So gate is fringing to the drain side, gate is fringing to the source side. This is overlap capacitance. What happens is that you have a gate, okay, you have an oxide here, but the source is coming like that, no, and the drain is coming like that, no. So this part, the overlap, this overlap is your gate drain overlap capacitance. You can call it COV or something else also, but this is your overlap capacitance. So this, if you look at the gate entire actual 3D block, so this depends, this scales with the W of course, but this depends on oxide thickness. So it very weakly depends, there is almost no dependence on the gate bias, but it depends on the oxide thickness, and it depends on the extent of overlap, this overlap, L overlap, okay. So that's overlap capacitance is there. This is the intrinsic gate capacitance here. This is your sidewall capacitance between the source drain region and the actually towards the channel, there is a halo implant. So the coupling of the source drain side, this is the source side, this is the drain side, the source and drain coupling to the channel, towards the channel, okay. There is this doping, the doping of the well here, right. So there is this sidewall coupling there. So this is CJSWG. CJSW is the coupling between the highly doped N plus source and drain, and through the shallow trans implant, which is an insulating region, it can couple capacitively to the P plus here from where the bulk diode is taken. This is a bulk or body diode, right. So P plus contact is there, no. So it will couple capacitively through the shallow trans isolation, that is one capacitance. This is your drain source coupling or capacitance through the substrate, through the bulk, and this CJ is the junction capacitance, the source N plus and the drain N plus couples with the well below. So that is your CJ, okay. So those are the capacitances, and if you look from the top view, this is side view. So if you look from the top view, you can see that this is the bulk or the body. So your drain is connecting coupling to the body, the source is coupling to the body, which is precisely this and this. Then the gate will couple to the body, the gate that is not immediately visible in the side view but a cross section, but in the top view you can see that. This is your CJSW, because it is on the 3 side, this side, this side, this side. The source drain N plus region will couple to to the bulk, to the bulk through the shallow trench isolation. Okay. This is the gate capacitance, the intrinsic gate capacitance is below. This is the overlap capacitance. The overlap capacitance can be C overlap. In some books they also call it CGSO, was it, yeah, CGSO or GDO. This is basically like the overlap capacitance between the source drain extension region and the gate. Okay, please keep that in mind. And this is a CJ that I talked about here, sorry, here and here. Okay. So the gate source overlap, the gate drain overlap capacitance, it's located on the source side of the gate along the W. That's what I meant. There is a small overlap precisely. It does not depend on VGS, but it depends on the extent of overlap, and it also depends on the width of the finger, because that will directly scale. Okay. There is also gate to bulk overlap capacitance, which is this. There are different expressions for all of this, which I am not writing it down here, but there are analytical expressions people have derived considering fringing also. Expression for fringing capacitance also has been taken into account, and people have expressed empirically, or with some mathematics with derivation also, as to the expression of these different capacitances, which I am not writing it down. It just suffices to understand that there are these different capacitances which need to be accounted for in the modeling or understanding or simulating a device, a circuit. Okay. And then finally we have drain to body and source to body capacitances. Now these capacitances, the source to bulk or drain to bulk capacitances, are very much dependent on the layout of the device, because you need different layouts. Layout optimization is a very rigorous and very important step, by the way. Okay. Layout has to be optimized for a specific application. The layout for maximum power gain may be different from a layout for minimum noise. When I say layout, how many number of fingers are you giving? Are you contacting the gate from both sides? How many VRs are you giving on each finger stripe or drain or source stripe? The overall geometry, that device geometry is very important. Okay. So there are three components of this source to bulk or body and drain to bulk or body coupling capacitances. One is CJ, which we already talked about here. CJ, this is CJ, which is basically like it's an area component. It's a junction capacitance, you can say, at zero bias. It depends on the doping in the well or the oxide. It depends on this, ignore this because we have not yet come to SOI, we will come to SOI. It depends on the doping in the well. So if you have this well, this well also may have a retrograde doping. So it depends on the doping of the well, and it is a zero bias capacitance. So it is like a N plus, and then there is a P region, P well. So this capacitance, this capacitance is the junction capacitance. That is great, not a problem. It depends on, of course, W and the contact width. Now there are two sidewall components I already told you. Okay. One of them is CJSWG, which is basically this, which is the N plus drain and N plus source coupling sidewise. Okay. Coupling sidewise to the towards the halo side, and then there is this on the shallow trench isolation side, it couples on the three sides, this side, this side, this side. Okay. So those we already talked about that. Okay. Now the expression for source bulk or drain bulk capacitances are also derived by people. This expression that I am writing you here is when the number of fingers is odd, the number of fingers is even. When the number of fingers is even, this is the expression, and it depends whether in an even number of finger, whether the outermost are source or drains. For instance, you have source, drain, even number of finger. Okay. Oh, sorry, this is gate, I am sorry, this is gate. So this is for instance 4 fingers are there, because there is 1 finger, 2 finger, 3, 4 gate fingers are there. There are 4 gate fingers. However, there is source, drain, drain, source. The source is on the outside. You can also have the other way, where you have the drain, source, drain. So drain is on the outside. This also has 1, 2, 3, 4 gate fingers. Okay. So you have 4 gate fingers, but source is on the outside. You have 4 gate fingers here, okay, but drain is on the outside. Okay. Got a point? Similarly, you can have odd number of fingers. So here you have 1, 2, 3, 4, 5 gate fingers, and in 5 gate fingers you have exactly equal number of source and drain. Source, drain, 3 sources and 3 drain. So if you have an even number of finger, then this expression holds true, and it depends on whether you have source or drain on the outside. For instance, this is source on the outside, this is drain on the outside. That is why it says CSDB. If S is on the outside, then this will hold true. If drain is on the outside, then this drain will hold true. Okay. So, this expression is for drain or source being outside for an even number of fingers. If there is an odd number of finger, then there is a slightly different expression. People have derived these expressions analytically, so we do not have to worry about that, but this is the source and drain bulk capacitance values. And apart from that, we already discussed about the other capacitances anyways, the overlap capacitances, right. So, we are done with all the capacitances. So, all these capacitances together, okay, all these capacitances together will decide your small signal performance. It will also decide your RF performance. The idea is that you want to minimize the capacitances without losing channel control, of course. So, how do you bring down the parasitic resistances and capacitances as low as possible for a high speed device application, for a higher FT or Fmax, for higher better noise performance, etc. Okay. So, with that we will come to a conclusion of this lecture. In this lecture we have talked about parasitic resistance, capacitances, we talked about charge quantization, capacitance, effective thicknesses, and quite a few other things that are pertinent to general purpose highly scaled CMOS or MOSFET devices, including those that are useful for RF application. The next lecture, which is going to be lecture 37, we are going to talk about small signal model for this kind of highly scaled nanoscale devices, and then we will probably talk about SOI, and there are many other things to also talk about multi-gate devices, architecture, and etc. Okay. So, thank you, and we will meet you in the next lecture.